we have been conducting over the last several years, me and my graduate students, on verification, validation, and uncertainty quantification of simulation models. There has been a paradigm shift in pretty much all scientific and engineering fields over the last couple decades, primarily induced by the improvements in the multiprocessor computing systems. As our computing power is increasing, our capabilities with numerical simulations are proportionally increasing as well. And in the old paradigm, we used to conduct a large number of experiments to determine the behavior of a system. And as a result of these large number of experiments, we would train empirical models to represent and perhaps use these empirical models in an interpolative manner. And in the old paradigm, we will use simulation models to understand why the experiments yield the type of data that they did yield. And basically, we will use simulation models to understand to understand underlying physics behind the observed behavior. In the new paradigm, however, is we're starting to need less and less experiments. Now we need a small number of experiments just to explore the physics and the mechanics of the problem, and then use this small number of experiments to calibrate simulation models and ultimately validate their predictions. The fundamental idea here is if you have a model, a simulation model that is calibrated and validated with respect to experimental data, then that gives us a very powerful tool that we can use to predict at settings where experiments are not feasible, and it can also allow us to reduce the number of experiments that are needed significantly. That obviously means incredible reduction in the experimental costs and perhaps significant time savings. And high consequence decision making is relying more and more on validated science-based model predictions. I guess the key word here is the term validated. Clearly, we cannot use a simulation model prediction in lieu of an experiment unless we are very confident about the predictions of this model, and that confidence comes from validating the model, and in fact verifying and validating the model using mature procedures or methodologies that have been developed and are currently being developed. The resource allocation is basically allocating the available finite amount of resources to experimental design and code development in a careful, in a very intelligent manner, such that we get the maximum predictive capability in our simulation model with minimum number of experiments. I'm going to go ahead and have two slides that basically go over the terms. It's almost like dictionary kind of slides that I would like to go over before I proceed with the presentation. It's just because that in the very beginning I want to make sure we all speak the same language. The term verification and validation sometimes used interchangeably in academic environments. But I would like to emphasize that there's a clear distinction between the two of them. Verification means that the model is solving the equations correctly. And basically the fundamental idea behind code verification is just making sure that your computer model is bug-free, it's running correctly, it's functioning as it's needed, and the numerical solutions, the discretization of the numerical solutions are sufficiently accurate, and our numerical uncertainties and errors are sufficiently low for the purposes of our application. So verification, in short, is trying to answer the question, are we solving these equations right? On the other hand, validation has a very different meaning. It basically tries to understand if the model that we have in hand is representing the real-world problem in an accurate manner for the particular application that we have in hand. Therefore, validation is trying to answer the following question: are we solving the right equations? If the verification is not done prior to validation, then even if you're solving the right equations, you're not solving them right, so you're going to get incorrect results. And if verification is done without validation, then you might be solving the equations right, but they're not the right equations in the first place. So what I'm trying to say is verification and validation need to go hand in hand, and they need to be, you can't have one without the other. Traditionally, in the current practice, verification has been done prior to validation as a first step, as a prerequisite, and traditionally the concept of verification and validation are handled separately in a decoupled manner. But there is a tendency towards coupling them and looking at the numerical uncertainties that are involved in the verification and parametric uncertainties and structural uncertainties that are associated with validation all in once and simultaneously. So uncertainty quantification then is the process of investigating the uncertainties in a particular problem, and obviously we're mostly interested in uncertainties in the predictions of the models in our particular presentation. We try to characterize uncertainties, we try to estimate them, and we also are investigated in how they propagate not only forward meaning from your inputs to outputs, but also backward meaning from your outputs back to your inputs. So in this context, uncertainty is pretty much everything that we do not know with absolute certainty. And any sort of natural variability, any sort of imprecision, natural variability of materials, imprecision in your measurements, just plain flat lack of knowledge of certain material behavior would all contribute to uncertainty in our definition. Okay, more definitions. So here the accuracy, the way I'm going to use the term accuracy is going to be describing the fidelity to data. In other words, how close are my calculations to the reference value? So you have a simulation model, and the simulation model will give you an output. It can be stochastic, it can be deterministic, but I would like to know how close that calculation is to the reference value. And of course, the reference value is the absolute truth. Here, precision means how reproducible the calculation is. Clearly, you're gonna have perfect precision if you do not consider any of the uncertainties in your input parameters. So you do have a level of uncertainty in your input parameters for any model, and if you consider these input parameter uncertainty and if you propagate it to your outputs, then you're going to basically determine how precise your model predictions are. So let me put these two things into an example. So let's say a clock is always 5 minutes fast, but it's always 5 minutes fast. So every single day it is 5 minutes fast. So that is not a very accurate clock, but it's very precise. It's not accurate because it has a 5-minute deviation from the truth, but it's very precise because every day it's giving you the result that is basically 5 minutes inaccurate. If you can determine that the inaccuracy of this clock is 5 minutes, you can compensate for it and basically correct what the clock is telling you. Precision, on the other hand, is the opposite. If you have a clock that is giving you negative 1 minute one day, positive 1 minute one day, so it's going 1 minute too slow and 1 minute too fast every other day, that's on average it's a more accurate clock compared to the first one, but it's not very precise because every day it's giving you something a little different. Confidence then is I'm not talking in terms of the statistical confidence here. I'm talking in terms of how confident you are that you will bet your own money on the predictions of this model output. So you gain confidence. You rely on a model as a scientist or as an engineer if you collect enough evidence that that model is going to be giving you sufficiently accurate data. So confidence is typically established through the procedures of verification and validation. Then credibility is if you have enough confidence in a model, then that basically transforms into credibility. Then if a model that you have a lot of confidence with will be a very credible model. I'm going to talk about two distinct features or processes that we regularly implement. The first one is parameter calibration. If the parameters of a model are not very precise, you can calibrate them and such that your model is predicting the experimental data better. However, I will caution everyone for just blatantly calibrating the parameters of their numerical models without having a proper understanding of the underlying inherent inaccuracy of the model. So parameter calibration can be, in the most rough sense, considered to be analogous to the precision issue. Bias correction can be considered to be analogous to accuracy. So bias correction is the inherent, so the bias is the inherent incapability of your model to predict reality. So just like the clock example, that clock is always 5 minutes late, so it has a 5 minutes bias. It's inherently incapable of telling you the truth. If you can figure out what that bias is, you can correct your model for that. However, you can't necessarily figure out what that bias is easily because your model also has some uncertain parameters. In short, parameter calibration and bias correction should be handled in a coupled manner. You should be considering both the uncertainties in your input parameters and the bias in your simulation model predictions at the same time. The reason they need to be considered at the same time is if you do not consider the bias in your model and just calibrate your parameters, you can tune your parameters to mathematically feasible but physically unrealistic values just to compensate for that bias. And that certainly will not give you a realistic model. Simulation will be then executing a model to produce any outcome, but I'm going to be using the term prediction for a very distinct meaning. For many of you, simulation and prediction may mean the same thing. However, prediction in our case means making a prediction with the model at a setting where we don't have an experiment. So you assume you have 5 experiments in the entire domain that you're interested in. So let's say you're interested in temperatures varying from 0 to 1,000 Celsius, and you were only able to collect 5 different experimental data points within that range. And prediction will be any sort of model output that you obtain at settings that are other than those 5 experimental settings. There are challenges in using numerical models in a predictive manner. So there are a lot of challenges in making this predictions that I just mentioned. One of the main reasons is that there are input parameters which we clearly do not precisely know what their values are. And I'm going to call them known unknowns because we know that they exist, but we don't know what they are. And then there's also something called unknown unknowns, which is perhaps our model is missing some important physics, such as maybe there's a friction that we need to consider, or maybe there is some material nonlinearity that we forgot, or there are some damping characteristics that we did not include in our model. And we don't even know that we don't know them, just because we didn't have the enough knowledge about the structure, we did not include them. So in this particular case, they're unknown unknowns. The term unknown unknown is not a very perfect term because there can be situations where you know the physics, like in the case of quantum physics, for instance, but you don't necessarily know how to incorporate it. So that makes it, then it also can result in incompleteness in the underlying physics. So unknown unknowns don't necessarily need to be unknown every single time. But the point I'm trying to make is we have some parameters that we are familiar with, but we just don't know what their precise values are. And there are also things that we are not familiar with. And all these things that we're not familiar with will also be penetrating as errors into our numerical models outputs. And on top of everything, as if this is not enough, we also need to worry about the numerical errors, the truncation errors, round-off errors, and discretization errors, and we would like to make sure we control them and we keep them as low as possible so that they don't interfere with our simulation results too severely. So if you're going to use a simulation model for any sort of predictive analysis, then we pretty much need to go through the formalized procedures of verification, validation, and uncertainty quantification. So that's a field by itself. It's a field of its own right, and it's a developing field. Basically, VVUQ means or covers everyone who are interested in making sure that their numerical models are yielding credible solutions that we can use for high consequence decision making. And what I'm gonna do is I'm gonna briefly talk about what verification entails and what validation entails, and right after that I'm gonna move on very quickly to a couple different examples that we have been working on. So code verification can the purpose of code verification in short is just to make sure that the code is doing what it's supposed to be doing. So it's just making sure that the code is bug free, and it's also can be considered to fall under the software quality and assurance procedures. And there are a couple of different methods for that. One of them is the method of manufactured solutions, and the other approach is using highly accurate closed form solutions to make sure your code is behaving in the right manner. So, for instance, you have a finite element simulation. You may want to build a say a cantilever beam and apply a point load and calculate the stresses, and from that back calculate the moments, and you have a closed form solution. You know what the moment should be at the support. So something like that could be considered as a closed form solution. The problem with that is the problem with both using closed form solutions is that it can only be applied to really simple problems where closed form solutions are available. The problem with method of manufactured solutions is you should be able to manufacture a solution. Method of manufactured solutions relies on one simple principle. If you're putting an input, you're going to get an output. And if you can take this output and put it in input, you should be able to getting the input that you started with. And if you can make an inverse of your numerical model, this idea works beautifully. But in cases where you cannot take the inverse of your models, that method of manufactured solutions is not an option. On the other hand, solution verification looks at the discretizations in the time and in the spatial domain. So solution verification wants to make sure we have a self-converged, a consistent model, self-converged and self-consistent model, meaning that if you refine your mesh size infinitely, you should hopefully be converging to absolute truth. And the one approach is to quantify the errors in your code verification and in solution verification and sum them in some meaningful manner to be able to quantify the total effect of numerical uncertainty. Okay, the validation, however, always requires experimental data. So because validation is trying to understand if this model is solving the right problem in the first place, you cannot validate a model without having real-life experimental data. And what kind of experimental data you should be collecting obviously depends on the problem type, but that is by itself a difficult problem on its own right. Validation primarily starts with test analysis correlation, is just collecting the right test using your engineering judgment and comparing the test results with your analysis, just to see if your model is in the ballpark in the first place. And then there are obviously a series of procedures that you can follow beyond that step, which I will be talking in a few moments. To be able to validate a model, you need to have some sort of metric to determine. So let's say your simulation model is telling you 5 Newton force when your experiment told you 4. Is your model valid or not? That by itself is a question that will require some engineering judgment, because you need to know how much accuracy you need from your model. And it will also depend on what kind of a model output you're dealing with. So in the example I gave you, it was a deterministic model output. It was a scalar value. But if you're dealing with, say, a mod shape vector, for instance, or a stress-strain relationship diagram, then in those cases it's harder to determine a single value for validation metric. You can use in the last bullet point I list fidelity to data type of metrics, which typically are distance-based and I can scalar values. You can also use regression type of metrics, which basically look at the correlation, for instance, correlation between two different mode shapes or correlation between two different stress-strain diagrams. Or you can also use statistical testing-based metrics as well. Okay, so I have my first example. I'm going to have 3 different examples here, and I'm going to really fly through them in the interest of time. But my first example will focus on wind turbine blades and will show how verification and validation be applied to wind turbine blade models. The objective for this particular application has been to demonstrate, or not demonstrate, but to see if we can use simplified numerical models for wind turbine blades. For those of you who might be familiar with this, wind turbine blades are fairly complicated structures because of their composite nature, and they have a large number of unknown input parameters. And if you try to incorporate all of those input parameters and all of these cross-sectional characteristics, it becomes a really difficult problem to deal with. And the question we were trying to answer here was, can we in fact use smeared cross-sections with reduced number of degrees of freedom. So what I have here, what I'm going to start with here is a simulation model M that has two distinct input parameters. So I have an X here and I have a theta. Theta refers to the parameters that are imprecise, and they happen to be also parameters that are influential. So my output Y sim is affected by those theta parameters, because if theta parameters didn't exercise any influence on Y sim, then we perhaps don't even need to worry about the parameter in the first place. X, however, represents the parameters that we can control during an experiment. For instance, let's say in an airplane you're interested in understanding the behavior of this airplane under different wind velocities and wind angle of attacks, and so then wind velocity will be your control parameter, and perhaps during your experiments you would like to look at the behavior of this plane at different wind velocities as well as angle of attacks. So in this particular case you have 2 different control parameters. I'm going to show you examples throughout the presentation that will have multiple control parameters. So a control parameter is treated and handled differently than a calibration parameter because it's fundamentally, its role is different. A control parameter adds a dimension to your problem. A control parameter allows you to investigate a system within its operational domain. So for instance, a nuclear reactor, say it's operating different temperature regimes, and different nuclear reactor cladding material is operating at different temperature regimes and different strain rates, and those 2 parameters are then your control parameters, and you want to make sure your model, your simulation output will be accurate at the settings of these 2 control parameters. So if your temperatures, if you know what the temperature regimes that you're interested in, then that's your target domain. You want to make sure this model will give good results throughout the entire domain, such that you can confidently use it. What I'm going to here do in the second step is I'm going to say my my observations, so my experiments are going to be giving me the truth, hopefully. Assuming that there is no bias error. So that's one assumption that we make. We're assuming that the experiments are conducted with rigor, and we can have experimental uncertainty, but we're assuming there's no bias in our experiments. And what we say here is that our experiments are the sum of the truth with a level of experimental uncertainty. Then what I do is I take I take the truth and represent it as the summation of my simulation model. So the simulation model you saw on the first line, and I add a term that basically represents model form error. So this line here is extremely important, because basically in this line, what I'm trying to say in layman's terms is, my model will give me a prediction. And this prediction will probably not be correct. That prediction will have some bias in it. I know, because no model is perfect and I can't build a perfect model. So I need to make peace with the fact that this model will have some bias. But if I can figure out what that bias is, I can correct for that bias and obtain the truth. So the idea is extremely powerful, and basically what it means is as long as that bias is a manageable level, in other words, you can't have too wrong of a model. As long as that bias is something manageable, we can pretty much identify what it is by exploiting experimental data. And once we do that, we can correct our model for the underlying bias and get predictions which are representative of the truth. So in the last step here, what I'm going to do is I'm going to take all these 3 lines that you saw above and combine them all together. And my final statement is that any observation we obtain will be a summation of simulations. Now I'm changing my term. I'm not saying bias. I'm going to say discrepancy and experimental error. This is very important here. I'm not using the same term anymore. I'm changing the symbol I'm using from model form error to a discrepancy term, meaning that model form error is the correct, absolute, true form of bias. Okay, I would, if I was God, I would have known what model form error is, but I'm not. And the only way to figure out what model form error is by doing experiments. But you cannot conduct infinite number of experiments. You need to conduct a finite number of experiments, meaning that you need to estimate what model form error is using a slightly imperfect version of it, which we call discrepancy. So the deviation between, or the difference between discrepancy and model form error is really critical, because we should be having a discrepancy that is close enough representation of model form error for the approach I'm talking about to be meaningful. Okay, so for the wind energy application, I'm going to briefly talk about 2 different studies. In the first one, the objective is to see how much we can simplify the model. And what you see here is 5 different models, and baseline is the most sophisticated case that has orthorhombic material properties and a composite layup and a biaxial layer orientations. And that basically yields 90 input parameters. 90 may seem like a high number. In fact, it is not, because if you look at the below figure, you're going to realize that we only considered here you can probably see 4 of them, but we considered a total of 6 different regions in this particular model, because two other regions are below. You don't get to see it here. But what I'm trying to say is that it's a really simplified representation. The number of input parameters could have been significantly higher than 90 if we were really trying to geometrically identically reproduce this model. So basically this trailing edge, this whole blue region in the figure has the same exact material properties, but that's actually not the case in reality, because the cross-section changes. As the cross-section changes due to taper, what kind of materials they use and how many of which composite you're going to have will change, and which will obviously influence the material properties in reality, but we ignore that for now. Okay, so we took some we took some field measurements from a Suzlon blade. That's about a 44 meters long blade. The reason we chose this particular blade was it's apparently a very common blade used in North America, and we used ANSYS software package to be able to develop the finite element model. And this is a really complex geometry. To be able to develop the finite element model for this blade, we had to get some help from other packages that are developed at Sandia National Laboratories for geometry development. And we, of course, completed a verification study to make sure we are obtaining converged results throughout the domain. And when we were doing that, we looked at root stresses and tip displacements. And when our simulation results converged, right at that point we said, okay, this is the number of elements we need, and that's how we decided our proper mesh size and mesh discretization. And then we looked at the discrepancy of this model. We looked at the discrepancy of the 4 different models that you just saw in the earlier table in comparison to the baseline model. So the baseline model is used to generate some synthetic experimental data, and the other remaining 4 models are used to compare against this baseline model. Again, this whole application was just to see how much we can simplify from the most sophisticated version to a simpler version. This simulation model was taking quite a long time to run, so we decided to build some surrogates. In this particular case, we used Gaussian process models as our surrogates. And its surrogate is basically a mathematical model that only represents the purely mathematical relationship between your input and output parameters, and it's a really fast-running model, so you can save quite a lot of time. And if you can develop an accurate enough surrogate, then you can save immense amount of computational time. And we did develop surrogates for this particular case. I want you to look at the middle figure here because that pretty much has all the information we need. In the middle figure, if you look at the red dots, you see the simulation data, and the blue dots give you the experimental data. And the purple bars give you the bias-corrected predictions, and purple bars also include the uncertainty in the predictions as well. So the point is the simulation model by itself wasn't predicting very well. There was a significant discrepancy, which is the third plot. The blue lines on the third plot, you can see how big the discrepancy was. So there was a discrepancy between the simulation model and experimental data, but by bias correcting it and by calibrating the input parameters in this particular case, we were able to make sure the model, bias-corrected model, reproduces the experiments. And we quantified how inaccurate each of these 4 different blades were using the tip displacement and the averaged root stress for this particular blade. Okay, and we quantify this model form error, or model form error, in other words, discrepancy in this particular case, using a volume representation. In the next study, we had again the same question in our minds. We wanted to see how simple a model we can use that will still be good enough, and without necessarily needing to wait hundreds of hours on a high-performance computing system to get any results. In this particular case, we focused on a prototype blade developed by Sandia National Laboratories. CX100 blade it's an exploratory study that has a carbon-reinforced spar cap, which is a fairly expensive material, but they would like to see if the use of a fairly expensive material can ultimately reduce the cost of the blade. Okay, in this case, we do have, we again built the numerical model. We made sure our mesh is really good, accurate, and it's not going to give high numerical uncertainties, and we obtained a mesh size of no more than 8 centimeters. We made sure shell 281 elements were going to be successful or appropriate for the type of application we have in hand, so we did a code verification on those. And we went ahead and used isotropic smeared materials for each of these sections. So the trailing edge section or leading edge section within itself has an isotropic smeared material. And we divided the entire blade into 6 different sections. What you see here are the experimental data collected at Los Alamos National Laboratory. The free is collected at Los Alamos National Laboratory, and the fixed free is collected at NREL, National Renewable energy laboratory. And so the fixed free and free data sets are basically collected to measure the nature frequencies and mode shapes of the structure. And we ultimately are going to use these experimental data to calibrate and validate our numerical model. So in the first, we wanted to make sure we exploit these two different data sets in a proper manner. So we use the first data set, which is the free experimental data, to make sure our parameters, our material parameters, are calibrated correctly. And then the second data set was reserved to make sure our boundary conditions were defined correctly. So I'm going to start with the free experimental data first, and afterwards I'm going to talk about the fixed free. Here you see a list of parameters that go into the model. We built a parameter identification and ranking table. So the PERT is an approach that has been developed in nuclear energy applications a couple of decades ago, and the idea behind developing a PERT table is to combine the uncertainty in a parameter with the sensitivity of the parameter. Because if a parameter is not uncertain, we don't necessarily need to calibrate that parameter. And at the same time, if a parameter is not very sensitive, or if the output is not influenced by this parameter to any significant extent, we don't necessarily need to worry about the parameter either. Because if a parameter is not very sensitive, even if it's wrong, it's not going to change the model output too much. So at that point, it's a safe parameter. We don't necessarily need to worry about that. So that's pretty much what we're showing here. That's a already reduced version of the list. So we've done initial PERT tables and reduced the list down to select few, and further investigated their uncertainty, which you see here in terms of lower bound, upper bound definition, and then we investigated their sensitivity, and which you see under the R-square value. R-square value basically means what's the percentage responsibility of this parameter to explain the uncertainty in the model predictions. As a result of this PERT table, you can decide to eliminate some parameters from further consideration. So if a parameter that is not very sensitive is by default eliminated, a parameter that's not very uncertain is by default eliminated, and so on and so forth. So we end up having only the parameters that are sensitive and uncertain, and those are the ones that have the green yes right beside them. The next step is about propagating the uncertainty to understand how these input parameter uncertainties are actually causing the model to make imprecise predictions. So the first thing you want to do is you want to make sure the input parameters that you identify, once you sample them within their plausible ranges, you want to make sure your initial simulation ensemble is predicting or is enveloping the experimental data. So in this particular case, I'm only showing you the first nature frequency here, and basically what we did was we went here and said these 5 parameters that have the green yes, and their lower bounds and upper bounds. And so I looked at their lower bounds and upper bounds, and I sample them. So when I sample them, in this particular case, we obtain about more than 4,000 simulations. So we obtain 4,000 simulations that represent various different configurations of input parameter values for those 5 calibration parameters that are identified through a PERT table. When we do that, we realize that the measured nature frequency is about 7.6 hertz, and our simulation output is basically enveloping it, and meaning that there exists a correct solution within those input parameter ranges that will give us the measured nature frequency with higher fidelity. Once the input parameters that need to be calibrated are identified, and once the experimental data is available, there are numerous ways of calibrating your model. So that going back to the parameter calibration discussion, there has been numerous publications in the past about how to calibrate numerical models to match the experimental data better. And one approach is obviously using Bayesian statistics. The other approach is optimization-based techniques. Several decades back and early on, a lot of people use trial and error-based kind of techniques where you tune the parameters of your model to see how the output is changing, and you continue doing it until the output matches your experimental data. What we use here is a little bit of a more sophisticated approach that combines Bayesian statistics with a sampling technique called microchain Monte Carlo. The beautiful part of this algorithm that we're using, which is developed at Los Alamos National Laboratory, where I used to work before Clemson University, is that it not only completes parameter calibration. In other words, it not only calibrates your input parameters, but it also bias corrects your model for you. So we're calibrating our input parameters while keeping the inherent inaccuracy or incompleteness of our model in mind, such that we make sure our parameter calibration is not compensating for other errors. So if we are successful, if the calibration results, calibration process is applied properly, then this calibration procedure can significantly reduce the uncertainty in the parameters. For instance, in the SPAR cap modulus, we started from a range that varies from 30 megapascal to 100 megapascal, but after calibration, after exploiting the experimental data, and after comparing our model against experimental data in a systematic manner, we're able to see that the SPAR cap modulus should in fact not be larger than say 60 megapascal, and it looks like the mean is around 40 megapascal. So that's a very valuable information, because it is reducing the uncertainty in this parameter will significantly reduce the output. Output of our simulations. The reason being, I'm going to go a couple steps back here. The reason being, SPAR cap has about 66% of the variability. So SPAR cap is responsible for 66% of the variation in the output, meaning that any sort of reduction we can obtain in the SPAR cap will cause a significant reduction in the predictions of this model. We not only calibrate one parameter, we actually consider all of them at the same time, simultaneously. So here what you see is we're able to calibrate the SPAR cap modulus and the trailing edge modulus, and we get a little better idea about the trailing edge density. The leading edge density and leading edge modulus are not calibrated properly at all. So we hardly gained any new information about the two of those. There can be many explanations for not being able to calibrate a parameter, and one explanation is perhaps these two factors, factor F and factor L, weren't sensitive enough, which in fact they are the lowest in the PERT table if you look at them carefully. Or the other explanation can be perhaps their ranges are not defined correctly. Maybe the uncertainty ranges, that minimum range and the maximum range that we identified using expert judgment or literature is not very accurate. So these two parameters certainly require further investigation. But we were successfully able to obtain a great deal of information about factor J and factor K. So when we do parameter calibration, we not only look at the individual factors. So in the previous slide, I was showing you the marginal distributions of these 5 parameters, which in this particular case, they're on the diagonal terms. But we also look at the cross correlations between parameters as well. So what that means is, if there is a hidden dependency between 2 parameters, then I should be able to see it in my cross correlation charts. So marginal distributions, and off-diagonal ones are bivariate joint distributions. And bivariate joint distributions are perfect ways to determine if there are any hidden dependencies between parameters. When it comes to calibration, you really do not want to have two parameters that depend on each other, or in other words, if you increase one parameter, if you reduce the other one, you get the same output. If something like that happens in an eigenvalue problem, for instance, if you only have one material, say you have a cantilever beam, and it's an eigenvalue problem, you have two parameters, one of them is Young's modulus, the other one is density. Unfortunately, you can find infinite configurations that are going to give you the exactly same nature frequencies. You do not want to have that. You do not want to have certain type of dependency. In this particular example, that's not the case because we have multiple parameters, and the relationship is fairly complex. It's not like a directly linear relationship. So what I would like to show you here is a comparison of where we started prior to calibration and where we are ending, and how much uncertainty we were able to reduce. So if you look at the prior uncertainty means prior to calibration, we had it, for instance, let's look at spark cap, Young's modulus, and our upper range, our lower and upper limits had a range of 62 megapascal. When after the calibration process, our 2 sigma range is only 23 megapascal. So there's a significant reduction in the uncertainty for this particular parameter, and the same goes to trailing edge modulus as well. So we were able to reduce the uncertainty quite a lot. We can't make the same statement for other three parameters, unfortunately. In this part I'm not going to spend too much time on, but we basically used the fixed free data set to be able to obtain information about how we can calibrate the spring constants that we put to be able to represent the boundary condition here. And that's actually a very difficult aspect model in real life because these structures are, the wind turbine blades are connected in a really complicated manner to their tower. We did a similar sensitivity analysis, we did a PERT analysis, we did the calibration. These plots are now very familiar to you, and we obtained, the only difference you see here is that we have a K value that we didn't have before. That's where my mouse is. The K value represents the stiffness constants for the boundary condition right now. And I would like to show you the how much better the posterior predictions match the experiments, which are the blue lines here after calibration. So before calibration, we were constantly underestimating. If you look at the red lines were constantly underestimating the experiments, but after calibration, we were able to obtain a better agreement. Once you calibrate a model, then that model becomes conditioned on the experimental data, and what you want to do is to make sure you test it against an independent set of data set. And in this case, we calibrated our model using nature frequencies, but then here we're making sure the calibrated model in turn can predict the mod shapes well. And this slide we are looking at right now is a comparison between the experimental and simulated mod shapes, and you'll see a fairly good agreement. There's a little bit of a disagreement here on the third mode, but we're suspicious that it's primarily because of the way the experiments are collected, and it's because the experimental measurement points and the points we extracted data from our model don't perfectly match, and we're believing that that's the primary cause for that deviation. I mentioned earlier metrics that are correlation-based. Model assurance criterion is one such metric that basically looks at the correlation between two different mod shape vectors. And if we quantify those MAC values, we obtain an average of 0.93 agreement. That's a very, very good agreement considering the fact that this is we're using experimental data. So that's that basically is giving a lot of confidence to us about the model predictions. I have about another 60 more slides. It doesn't look like I'm going to be able to go over all of them. What I'm going to do is just spend maybe 2 minutes on each of the examples without getting any more of the details. Example number 2 was about another project of mine that is ongoing, and it's funded by Department of Energy. And this particular project is focusing on developing frameworks for code developers and engineers and scientists to be able to validate their simulation models. And the fundamental idea or the fundamental question we're trying to answer is, if you have, say, $1 million and you can use that $1 million to collect more experiments to make sure you calibrate your model better, or you can spend that $1 million to sit down and in front of your computer and code and improve the inaccuracies in your model and maybe add more physics, the missing physics into your model. It's a really hard question because we don't really know which one will benefit the problem more. And we have been looking at the model predictions and how well they match the experiments and so on and so forth. And we have been developing strategies to tell decision makers how to spend their money. So if you look at this particular case, for instance, this framework, again, we don't have too much time, but I want to spend maybe 30 seconds on it. This framework summarizes everything I've been talking about for the last almost hour. We have code simulations, we have physical experiments, and we calibrate them. We calibrate our parameters and we bias correct for the incompleteness of our models. We do parameter calibration as well as bias correction. Once we do bias correction, by default we determine what the bias is in our model, and that bias is a very, very important thing to know, because if you know what the bias in your model is, then you know how incomplete your model, how inexact your model is, which means, oh, you can go ahead and correct for that, but if that bias is really, really high, can you really trust that model, and can you really use the model predictions in any meaningful manner? So what we say is, if that bias is not sufficiently low, okay, so what we say is that bias, first of all, should converge. Okay, so for us to be able to determine that bias correctly, we should eliminate the parameter uncertainty to the maximum extent. So once we do that, once we make sure the parameter uncertainty is handled, then, in other words, the discrepancy bias is converged as the number of experiments increases, then we look at how big that remaining biases. And if that bias is sufficiently low, this means the model is good enough for our application. But if the bias is not sufficiently low, then in that case we say you should go ahead and improve your physics. So looking at whether the discrepancy is converged or not, we can tell them whether they should go ahead and do more experiments on looking at how much that discrepancy is in the end of the day. We can tell them whether they need to conduct more code development or not. So we have developed numerous strategies in the past. I'm going to skip these, and we have applied these strategies to various types of models and demonstrated their applicability. As I said, I have about let me just go ahead and go through these slides really quickly. And perhaps I want to show you one slide only. What I want to show here is this model is developed at Los Alamos National Laboratory. It's a material model. And this particular model, we have calibrated it. We had a total of 11 experiments, and we calibrated this model using 1 experiment only, then 2 experiments, and 3 experiments, and all the way up to all 11 experiments. And we looked at how the discrepancy is converging, because the more experiments you use, the better you're going to be able to calibrate your parameters. Therefore, your parameter uncertainty should be reduced significantly. Therefore, you should be able to estimate that discrepancy bias accurately as well. And ultimately, for this particular application, we had a discrepancy bias of 200% for one of the texture predictions and about 50% for the other texture prediction. and we concluded that these values were way too high for our application, and as a result of that we decided to improve physics, and our collaborators at Los Alamos National Laboratory worked on it for 2 years and added more physics into it, and as a result of that we repeated the whole procedure, and we obtained outputs that are significantly improved. So if we use the exact same 11 experimental data sets, we realize that the predictions are significantly improved compared to the previous version of the model. So I think it's a good place for me to stop and accept questions for the next 2 minutes if there are any. It looks like I completely overestimated how many slides I can go over during this time frame. So are there any questions, or I'm keeping my eye on the chat window. I'm not receiving any questions so far. We have 1 more minute. If you want me to clarify anything, or if you have a particular problem that you're interested in applying V&V techniques, you can certainly email me. My email address is sez@clemson.edu, and you can also easily find me Clemson University's Glenn Department of Civil Engineering Directorate that I'm of course listed as one of the faculty, and my email address and contact information is there as well. Please feel free to email me or call me if you end up having some questions about this presentation, or if you would like to apply any of these techniques in your applications. Otherwise, I think this is going to conclude our presentation. Thank you.
Thank you, everybody, for attending our MIDAS technical webinar. If you guys have any questions, then feel free to contact Professor Caesar, and also you could also contact me if you like to become a next speaker for us. Thank you.